So with this video, we're going to start talking about the third phase of this course, and this is going to be the most significant part of our statistical computing course. Um, so far, we've been generating data or generating observations from the computer such that they follow certain distributions. That was a particular task that we are going to call sampling, as in we were using sampling methodologies. We'll come back to the idea of sampling methodologies for other tasks later on towards the end of the course. But now we're going to start talking about optimization. Okay. And so that's the other main place where statistical computing becomes involved in many topics in statistics. So, like I said, we're going to start talking about optimization from now on. And although there are various optimization problems that are present in statistics, one of the major ways that optimization is introduced or is pertinent to statistics is via the problem of maximum likelihood estimation or the maximum likelihood estimator or the MLE. So one common use of optimization comes in this. Now, you should be familiar with MLEs or maximum likelihood estimates already, but in this video, we're going to do a little bit of a quick introduction to MLEs, just so we're all familiar and we've reviewed, what the actual task in maximum likelihood estimation is. Okay, so we start talking about maximum likelihood estimation. Now, again, just to remind us, we are no longer going to be talking about artificial data that is being generated on a computer. That was something that was happening in the first or second parts of the course. We've now pivoted to real data and real data understandings. So, with that thought, suppose x1 up to xn is a random sample from some distribution with density f of x given theta. Okay. That means this is my random sample and it comes from some density f of x, where this given theta over here means that this is a parameter that's pertinent to the model. Okay, or parameter that we might be interested in estimating. And this particular parameter, theta, takes a value in capital theta. This I'm going to call the parameter space. Okay. Now, again, x given theta implies that given a particular value of theta, f given theta, so f dot, meaning you can put anything here, defines a density function. Okay, that's what f given theta means. Now, the parameter theta can be a vector of parameters, so it could be multiple parameters, theta 1, theta 2, up till so on. It could be a single value, a scalar quantity as well. Now, after having obtained this real data, this x1 up to xn, from some distribution f, where this f is similar to before, is a distribution with density f of theta. Okay. What we might want to do, having observed data, is use the data to estimate theta, to understand what type of values theta takes to get a good guess for theta. And we would also like to construct confidence intervals or understand the variance of the estimator theta, right? So just a point estimate over here is not going to be sufficient for us to understand, what values theta takes. So we would like to construct maybe confidence intervals around theta to understand a little bit more about our estimator. And a useful, in fact, a go-to method of doing this is the maximum likelihood estimation method. Okay, so let's take a quick look now at what MLE or maximum likelihood estimation is. So let bold X be the vector x1 up to xn. So this is bold X represents all of our data, right? Now the idea in maximum likelihood estimation is first that we define something called the likelihood function. So the idea is that we define, and I'm missing a word here, we define a likelihood, okay, a likelihood function L of theta given x, such that it measures how likely a particular value of theta is given that we've observed the data. Okay, So L of theta is going to measure how likely is this value of theta. So it's a function of theta, and it will measure how likely is this value of theta given the x's, the data, the actual data that I've observed. Okay. So in general, L of theta given x equals small x. So this notation over here means that this is the random variable, right? And this is the actual value observed. Okay. So in general, L of theta given the actual value of the variable or data observed is nothing but the joint distribution of all the x's. There's a typo here. So that means L of theta given x is nothing but f of the density function, the joint distribution of x given the particular value of theta. Okay, which x is nothing but the tuple of all the data observed. So it's f of x1, x2 up until x1 given theta. So actually the likelihood function is nothing but the density function, the joint density function of the data observed given that value of theta. The difference is that the density function here are functions of x's, but actually what we're doing is we're now constructing the likelihood function L theta to be a function of theta. So now our x is going to be fixed on what is the data that I've observed, and theta is what will change based on where we are evaluating the likelihood. We'll see an example of this very soon. But now we can go a little bit further as well, is when the sample is indeed independent. That means, so what do I mean by independent here? I mean that when x1, x2 up until xn are IID from F, okay, so they're independent and they're also identically distributed, well then this thing can decompose into individual densities. So this likelihood becomes L of theta given x becomes the product of I going from 1 to n, f of xi given theta. Okay, and this becomes our likelihood function. Okay. So this basically tells us that, okay, if I want to look at a particular value of theta and I say, well, how likely is this value given all the data that I've observed? Then this is nothing but, well, what is the chance that I would have seen this data given that this was the value of theta, right? So what is the chance that I would have seen this value of theta, this xi value of theta, given that this is the particular value of theta that I have proposed? Okay. It is important to note that L theta x is not a distribution over theta. So it's natural to see that each of these densities is a density as a function of the x's, but L is not a density and does not describe a distribution as a function of theta. It is just a function of theta. It doesn't have to integrate to 1 because we would integrate over theta if we were to, and not over the x's, which is what we do here. Okay, so that's something to keep in mind. And now when we have the idea of, okay, how likely are different values of theta? So let me just write that idea down. So this basically says how likely are different values of theta given the data x observed. So this is what the likelihood function measures. Now we have an understanding, if we have this function, then we have an understanding of how likely are different values of theta. So then we can ask ourselves, well, what is the value of theta that gives me the largest likelihood? So which value of theta is most likely? And that is the maximum likelihood estimator. So the most likely value of theta, having observed the data, is the value that maximizes this likelihood function. So theta hat MLE is nothing but the argument that maximizes the likelihood function over my parameter space of theta, capital theta. Okay, so theta hat MLE is the value of theta that gives you the largest likelihood. Okay, and theta hat MLE is called the maximum likelihood estimator. Now, as you can understand, maximizing the function L theta may be complex for some problems and may be not possible to do analytically. So the idea is that that we are going to, that we are going to have to find where this function is maximized. And it's possible that L theta given x, this function looks fairly complicated. It's possible it's not that easy or well behaved. Okay, so which means that we're going to have to figure out how to actually maximize this. Now, in some problems, this will be easy to do, and we'll go through some of those situations in this video. But often, this becomes not possible to do with pen and paper. It's not possible to do what you call analytically. So we need some numerical techniques that can do this without actually having to solve the maxima problem. Okay. So this is where we're going to start learning about numerical optimization methods in a few videos. Okay. But before we do that, we have to understand what type of functions we're going to be looking at. So the first definition pertaining to this is that of a concave function or a one-dimensional function. Now, there are many ways to define a concave function, but this is the way I'm defining it. A function h of x is concave if its second derivative is less than equal to 0 for all x. And if the equality never holds, it is called strictly concave. Now, the second derivative being less than equal to 0 means that the function should look something like this. So the second derivative everywhere, this is the space x, this is h of x, and the second derivative everywhere over here, h double prime x is going to be less than 0. Okay. Similarly, if I take a function like this, then this function has the second derivative of x actually greater than 0, and it's called a convex function. Okay. So we have concave function that look like that we're trying to maximize something, and convex function that look like a bowl. Right? So naturally, if you want to maximize an objective function, or if we actually want to maximize a function, then we would like it to be concave so that there is one unique maxima. So if a function is strictly concave or concave everywhere, then it has only one maxima. So let me write that down. If function is strictly concave, it has a unique maxima. Okay. And that's exactly desirable for our target functions, L functions, because we would like to hopefully not have the function look very complicated. An example of a complicated function could look something like this, where a function like this, h of x, can be less than 0 or greater than 0 based on x. Sorry, not h of x, h prime x. Can be h double prime x, the second derivative can either be less than 0 or more than 0 based on what the value of x is. And I should say greater than equal to 0 or less than equal to 0. Okay. And so in orange, there is a function there that is not concave, not convex. It's fairly complicated, and we don't like those functions in terms of optimizing them. Because if you're trying to find a maxima of those functions, then that maxima can occur here, here, and here, and we don't know where it's actually occurring. So we'll get into some of these concepts in more detail soon. On the other hand, we also would like to be dealing with target functions that are in higher dimensions. That means the x is actually a vector input, not a unidimensional input. So a function h of x is concave if the Hessian of the matrix, which is the second derivative matrix, is negative semi-definite for all x, which means that if all of the eigenvalues of the Hessian matrix are non-positive, then that matrix is a concave, then that function is a concave function. Okay, so we'll be getting to this and using these definitions in more detail later on. Okay, but actually, let's first try and understand what do likelihood functions actually look like, and can we maybe visualize them? So visualizing log likelihoods and MLEs. So here's an example. Suppose I have two data points, x1 and x2, IID, so they're independent, and they're both from the same distribution of normal theta comma 1. Okay, and we don't know theta, so that means that what we want to do is estimate theta, right? We don't know it and we would like to estimate it. And suppose the actual data that we observed was x1 took the value 2, so I denote that as small x1, and x2 denotes the value 3, and I take that as small x2. Okay. Now, having observed this data, this is the data that I have observed. Right? So I have observed this. Having observed this data, I want to think about what value, and given the fact that this is my distribution, I want to know what value of theta can be quite likely, right? So I saw x equals 2 and I saw x equals 3. And my distribution that x is coming from is normal theta comma 1, and I want to know what kind of values theta can take. Well, if I think about it, then if I consider theta equal to -5, that seems like a value that is probably, if that is the value of theta in this normal distribution, then it doesn't seem like I would have generated these two data points, right? If theta was equal to -5, so the mean of the normal was, let me write this in, right? If, say, theta is equal to -5, okay, then and that means the mean of the normal distribution is at -5. And what I observe are values x equals 2 and x equals 3, right? So I observe these values of x. Well, then it looks like these values of x would probably not come as actual draws from this distribution if theta was indeed -5. So clearly theta equals -5 is an unlikely value of theta, right? So the function should give it a low likelihood, a small likeliness, right? Well, so let's say I consider, theta equal to 5. Well, that seems certainly more likely than theta equals -5, because if theta is equal to 5, then yeah, it's possible that 3 and 2 are actually generated draws or actual real data from a normal 5,1 distribution. Okay, maybe not very likely, but still fairly much more likely than this draw. But actually, what would be really likely for these two draws is if theta was somewhere here, right? If theta was somewhere here, then we would certainly think, okay, theta is somewhere in the middle between 2 and 3, and then 2 and 3 are going to be very reasonable and quite highly likely draws from this distribution. So I would guess that theta is somewhere between 2 or 3, so not divided by 3, 2 or 3, right? And maybe right in between them, like 2.5. This is the idea of the likelihood function, and I'll show you a plot in a bit. But it basically tells you, well, how likely are certain values of theta given the data that I have observed? Okay. Mathematically, we know what the definition is. L of theta given x1 and x2 will just be the individual products of f of x1 given theta and f of x2 given theta. But now again, recall, this is conditional on the actual data that I've observed. So That means I actually put in the value of the data that I've observed to give me a function of theta. So I'll get f of 2 given theta, which is x1, and f of, okay, this is a typo, this should be 3. Okay. F of 3 given theta. And now this now is just individual densities, which I can multiply using the density of a normal theta comma 1. That gives me 1 over 2 pi e to the power minus 2 minus theta squared by 2 and minus 3 minus theta squared by 2. So this is the final likelihood function. Now, often calculating either the likelihood or maximizing the likelihood can be a little troubling because you can see that this is e to the power something. So taking a derivative maybe in order to maximize can be a bit challenging. So often what will be more useful is if we take a log, right? And we'll again get to how do you actually, why does this actually work in a little bit. But we take a log, and so L theta is equal to log of capital L theta given x1, x2, which if I just take log of this is minus log 2 pi, minus 2 minus theta squared by 2, minus 3 minus theta squared by 2, which is basically just a quadratic function, right? Now what we'll do is we'll plot this function. So this gives us our actual log likelihood. Okay, we'll plot this function to see which values of theta are likely, which values of theta are do we expect to actually have given this data. And when I do that, when I plot it for, so this plot is the exact, is exactly this curve over here as a function of theta. So as theta changes, I get different values of of how likely is the function. So this over here is L of theta. And so as you can see, theta equals 5 is given a very small likelihood over here. It's not a big likelihood. Means, okay, theta equals 5 is not as likely. For example, theta equals 4. Theta equals 4 is much more likely. Okay. And actually, theta equals 3 is much more likely because we observed data 2 and 3. And similarly, theta equals 2 is quite likely as well. But in between those, what the value that maximizes the theta is actually the value right in the middle over here, which gives me, in this case, the theta hat MLE, which is the argument that maximizes the log likelihood in this case, or the likelihood, right? So this gives us, okay, well, this is the value of theta that seems the most likely having observed the data that I have observed. Okay? This is the idea of a likelihood function. Let's do another visualization of what the likelihood function looks like, or what does it mean? So what one has to understand also is these are two random observations that data points that I could have seen from normal theta comma 1. Now, I could have, every time I do this experiment of, let's say, going and getting new data from this population, whatever is the population, I'm going to get different observations. They're not always going to be x1 equals 2 and x2 equals 3. They're going to be a little bit different every time, right? Because it's random observations. And because they're going to be a little different every single time, I'm actually going to get a slightly different curve every single time, because sometimes these two values will be different, which means if these two values are different, means these two values are different, means these values are different, which means this and this is also different. So the whole shape of my curve is going to change based on the actual data that I have observed. Okay, this is the feature I want to elaborate on in this next example. So consider the same normal theta comma 1 distribution. And suppose we obtain one data point from this distribution, which means I just get x1 from normal theta comma 1. Okay, And what I do is I calculate the log likelihood, right? So the log of theta given x1 is log of f of x1 given theta, right? For whatever is the x1 that I observed. Now, what I'm going to do is I'm going to repeat this process again. I did it once and I got some x1, but I'm going to repeat this again. So every time we obtain different data points, we will get different log likelihood functions, which means the log likelihood function is also a random quantity that changes based on the random data that we are observing. Okay. Now I can also do this process instead of for just one observation, I can do it for 100 data points or 100 observations. So if I get random data points from normal theta 1, 100 of them, then the joint likelihood log of L of theta given the data is just the summation of log of f of xi given theta. So every time I now get what I'll do is I'll get a new data set of 100 points many times. And every time I get a new data set, I'll get a new shape of the log likelihood function. Okay. And we'll get a different log likelihood function every time. And what I'm going to plot now is the log likelihood function divided by n for each of those data points, for each of those data sets. So in every simulation of getting a new data set, so here I'm just mimicking a real life situation where I could generate new data. I'll do it in R. And what I'll do is I'll plot the log likelihood divided by n. Now we are only dividing by n here because what I want to do is I want to compare this log likelihood with this log likelihood. But this log likelihood is constructed from one data point and this likelihood is constructed from n data points. So in order to compare them, I'm just dividing by n. Okay. And this is exactly what I'm going to get. Okay. So in red are all my different data sets, the log likelihoods of all the different data sets that I generated with only one observation. Okay. And you can see that each of these is a different curve, the red curve that has quite a bit of variability. Right? Every new data that I get describes a new likelihood function because it's a data set of size 1 every single time. Okay. So I'm doing we'll not do this in real life. We're not going to get new data set in real life all the time. I'm just doing this to show you how the log likelihood function changes every time. Now, if I zoom in to this log likelihood function, okay, then this log likelihood function has a maxima, okay, and that maxima happens here, okay. So its maxima is happening, oops, right here somewhere. And so what I'm going to do is I'm just going to draw that line down on the x-axis. Okay. Similarly, the log likelihood function here has its maxima occurring somewhere here. Okay. And everywhere in between, there are so many curves that actually have their maxima in red, that actually have their maxima happening somewhere there. So this would be theta hat MLE for the first, let's say the first data set of size 1. And this would be the theta hat MLE for the second data set, if I'm just doing this process again and again. Now you can see that this process gives us so much variability in what theta hat MLE would be based on likelihood to likelihood, right? And this corresponds to n equals 1. So when you have a data set of size 1. Now let's actually look at what happens when I have larger data sets, data sets of larger size. So now I'm looking at data sets of size n100, which is the blue curve. Now these now have information coming from 100 different data sets, which means that they have a lot more understanding of what kind of values are more likely for theta, right? So now that I've seen some more data, the likelihood function moves around less so because I've observed more data and I have more information about what values of theta are more likely. So if I look at any of these functions over here, well, all of their maximas is pretty much occurring maybe somewhere here to somewhere here. So for n equals 100, if I were to look at the maximum likelihood estimates, well, they only have variability in that short window, right? Not really outside that window. Okay, which means, so what does this imply? This is really implying that as n or data size increases, the MLE estimates have lesser variance. Right? As your size of the data increase, the maximum likelihood estimates have less and less variance. They become more and more stable and more what you'd call robust. Okay, and this really demonstrates the idea of the good behavior of maximum likelihood estimates. That when you give me more and more data, I'm going to give you better and better estimates, and we'll get to this property as well. Okay, this is really what I describe in this text over here as well, right? Okay, so this was, I just wanted to make sure we understood what the likelihood function is and what the idea of maximizing the likelihood means. And in the next video, we'll go over a few examples of maximum likelihood estimation.